Alright guys, we are continuing with our discussion of the lab devoted to synthesizing aspirin. As I mentioned earlier, I decided to sort of expand and modify the procedure in order to include recrystallization of aspirin, to explain to you why organic chemists in particular spend so much time in the laboratory while making a substance may take a fairly short period of time. A lot of time is spent to actually purifying the product. The thing that you may or may have noticed when we looked at the reaction used to make aspirin, I deliberately left it out, but now I'm kind of bringing your attention to it, is the fact that I have two arrows going back and forth here. And there is a lot of information in these two arrows, and it's not a coincidence that they're there. So you may recall that in chemistry, when two arrows appear like this represents so-called reversible reaction, which means as soon as products of the reaction between initial reactants are formed, the products may react with each other, producing reactants again. So you have basically two competing reactions taking place at the same time. You have a forward reaction where reactants are turned into products, but you also have so-called backward reaction where products react and form initial starting materials. And so the fact that this reaction is reversible, like vast majority of organic reactions, I would say probably about 95% of all organic reactions tend to be reversible. The consequence of this is when you stop the reaction mandatorily, like with more than about 15 to 20 minutes of heating, you basically have a situation where you know that your product is not going to be pure. Now, what you have done, hopefully by now when you're watching this video, after you heated your salicylic acid with acetic anhydride in the presence of strong acid, you took the reaction flask out of the water bath, you cooled it on the bench, and then you placed it in the ice bath. Placing it into an ice bath, and addition of a little bit of water caused crystallization to occur. Now this right here, acetylsalicylic acid, is the only product that is expected to be solid. The second product, acetic acid, as we all hopefully know, is a liquid. So liquid would not be obviously crystallizing. And so ideally you would only have acetylsalicylic acid, but because reaction is reversible, we probably would expect that some of the unreacted salicylic acid would also crystallize alongside our product, our desired material, our aspirin. And so what we have in our hands after crystallization and filtration, the liquid product materials like the anhydride and acetic acid, all dissolved in water, would be separated from the solid. But the solid would then contain both aspirin and unreacted salicylic acid. And that requires us to perform purification. The procedure used for purification discussed in the handout that hopefully you have printed and will have available for lab discusses the fact that recrystallization is a method employed by chemists that's based on different solubilities of the desired product and undesired impurity, like in our case salicylic acid is undesired impurity. And so it's based on different solubilities of desired product and undesired product in a certain solvent. For us, that certain solvent will be alcohol, ethanol to be specific, or ethyl alcohol. It's well-known fact that salicylic acid dissolves in ethanol better than acetylsalicylic acid. And so we're going to take our crude product, we're going to add some ethanol, possibly with a little bit of heating to help it dissolve faster. I would point out that because ethanol is used, ethanol is flammable, so no Bunsen burner should be present, no open flames, period. Only hot plate should be used to warm up a mixture. So when we add ethanol to our crude product and heat, both salicylic acid and acetylsalicylic acid will dissolve But then we're going to take that solution and we're going to put it on ice and we're going to quickly cool it. When we cool it quickly, the material that's less soluble, which in our case is salicylic acid, is going to crystallize, while a material that's better soluble in ethanol, namely salicylic acid, will stay in solution. And so this quick cooling will then allow us to separate acetylsalicylic acid, which is expected to crystallize, from salicylic acid, which is expected to stay dissolved. The key word here is quick cooling and quick filtration, because if you wait too long, you're risking having your aspirin being contaminated with salicylic acid once again, because the longer the cooling and filtration, the greater the chance of salicylic acid getting dissolved, getting crystallized alongside acetylsalicylic acid. And so you will quickly cool and filter, and hopefully this will allow you to separate your aspirin from undesired impurity, which is salicylic acid. Of course, I would point out that doing this only once would probably not completely rid your product of undesired starting material, but hopefully you will be able to see the progression. In real life, this recrystallization would probably have to be done at least 3 to 4 times to achieve proper purity. So next we're going to discuss testing. And there will be 2 tests that you will have to perform. First of which is a test with a substance called ferric chloride, FeCl3. Ferric chloride is a yellow, will be used as a yellow solution in alcohol and water. And the reason why FeCl3 is used is to test for phenol group. Now, regardless of what your lab manual says, in the lab manual, the explanation for this portion is sort of confusing. I'd like you to just remember that FeCl3 is used in organic chemistry to do a qualitative test for phenol. What does it mean, qualitative test? Well, basically whether it's there or not. So if phenol is present in an organic molecule and you add a FeCl3, typically you get color change. Phenols are colorless in solution. FeCl3 is yellow. Whenever you get color change, I wrote purple here because that's exactly what we are looking for in this particular case. It may be some other color depending on the structure of the phenol, but the point is the color will change if phenol group is present. If there is no phenol, color will not change at all. So here you're going to be testing various samples. The test is very simple. You're going to take a spatula full of the solid that you're testing, place it in a clean test tube, and add several drops of ferric chloride solution that will be available in the hood, and then check and see what kind of color change you get or don't get. So what kinds of things are you going to be testing? Well, they're listed right here. Normally, if you were here in class with me while I was doing this, I would be asking you to try to make some predictions based on the structures you're seeing and based on what we've discussed already, whether or not you're going to see, or you would expect to see some color change here upon addition of FeCl3. Starting with original or unreacted salicylic acid. So salicylic acid is a substance that's used here as a reactant, and obviously you can see phenol here. And we discussed the fact that salicylic acid does contain phenol, so you can make your own conclusion as to whether or not you would expect a purple color here. Next would be crude or unpurified aspirin. I want to point out that before you start recrystallization, hopefully you'll be reminded by TAs in the lab to save a couple of spatulafuls in a separate beaker or test tube for testing. So not all of the crude aspirin you're able to obtain in the reaction should be used here for recrystallization. Some of it needs to be saved for testing. Like I said, you only need 1 or 2 spatulafuls, that's all. So will we see any purple color for unpurified aspirin? As I discussed, the fact that reaction is reversible hopefully explains to you what you might see here. Next will be the purified aspirin. So this will be the aspirin obtained after recrystallization, and whether or not you will see any purple color depends on how well your crystallization went. And hopefully, if you don't see complete absence of purple color, at least you will see lightening of the purple for purified versus crude. And then finally, what we will also do, what you will see in the lab, is we have some commercial aspirin tablets which we grind and place in a hood for you. It's basically commercial aspirin ground up. So assuming commercial aspirin is completely pure, you can again make your own conclusion as to whether commercial aspirin should turn purple in the presence of FeCl3. The second test you're going to do is a heating test. And here we need to talk about why you're doing it, what is happening, and what is the sort of observation that you're going to be making and what that observation actually means. So you're going to take some of the aspirin. You can use either a crystallized or crude aspirin, it doesn't matter. You're going to put it in a clean, dry test tube. A large test tube is probably better. You're going to safely grasp the test tube with your test tube holder, and then you're going to heat briefly the contents of the test tube in the flame of the Bunsen burner. Before you light the burner, please ensure that no one in the lab is still using ethanol for recrystallization. And heating should be done in a safe fashion, meaning mouth of the test tube pointing away from yourself and others. Heating should take only a couple of minutes, maybe even less. Usually it causes the solid to sort of liquefy, and then you're expected to very carefully smell the contents of the test tube. Now let's discuss what's going to happen when you heat. You're going to heat just aspirin in a test tube, nothing else. And yet I'm showing the other reactant here, and this of course you will recognize as water. So where does water come from? Well, the answer is it comes from the air. Air tends to contain a certain amount of moisture, and usually at the end of summer and early fall it's fairly humid, and so there's plenty of moisture in the air. And heating here is basically used to speed up the reaction that will occur between aspirin and water even at room temperature. So heating is basically to speed up the reaction. The reaction we're looking at is between aspirin and water. And another important definition I would like you to know after this is definition of hydrolysis. I wrote it in red right up there. Hydrolysis in general means reaction of a substance with water. So in this case, aspirin is going to be reacting with water. What's happening in the course of reaction is schematically shown here. Once again, this oxygen, which is right now part of ester group, is labeled with an asterisk. I'm showing hydrogen separating off of OH group in water, and hydrogen attaching itself right here to this oxygen. Hopefully this structure now looks familiar because we've talked about it so much. So now you have a hydrogen again attached to the oxygen, regenerating or reforming the phenol group that we've talked about in producing salicylic acid once again. Would you be able to detect salicylic acid specifically by smelling? The answer is no. Salicylic acid is a white solid that does not have a smell to it. But the reason why you're asked to smell is because of the second product that's formed. This portion of what used to be aspirin, CH3C double bond O, gets attached to the OH group left over from water, and as a result you get CH3C double bond OOH, which you hopefully recognize as acetic acid. And so acetic acid being produced allows you to tell that hydrolysis is occurring by smelling the test tube contents, because acetic acid, of course, has this unmistakable vinegar-like smell. And so by smelling the heated aspirin and detecting vinegar-like smell, you can basically assert that hydrolysis has indeed taken place. Now, you may recall when we did synthesis, you were instructed and hopefully reminded by your TAs when you were heating your reactants in hopes of producing aspirin. Hopefully you were told to take a small piece of parafilm and loosely cover the mouth of the test tube. Now, you typically never cover containers that are heated, but loosely covering your container here is fine, and that's because obviously your water bath, boiling water produces water vapor, and you can see here that water vapor entered the reaction flask and would start destroying your aspirin, hydrolyzing it on contact before you were actually even able to isolate it in the course of your reaction. And so here you hopefully now see why you were told to loosely cover the mouth of the flask while making your aspirin. One other thing I'd like to point out, which is very, very important, I always try to show you how things we do in lab sort of relate to your everyday life. And here, there's a very important lesson for everyone. Very often people keep medicines, including over-the-counter medicines, in the medicine cabinet in the bathroom, and it may not be such a good idea, and this equation explains why. Bathroom, of course, that happens to be the most humid place in the whole house, and you can see that water vapor can easily penetrate the bottle with your medicine, regardless of how tight it may appear to be closed. And in the case of aspirin, it actually will hydrolyze aspirin and produce a substance called salicylic acid, which we discussed earlier, presents potential danger if people ingest it because it can cause stomach bleeding and ulcers. And so a couple of things. First of all, it's not a good idea to keep your medicine where it's humid. Second of all, it's never a good idea to take medicine that's expired, because it means it has been exposed to elements for a long time, including water vapor. And third of all, let's say you may, or some of your maybe relatives, may have some aspirin that might be sort of close to expiration date and has been stored in humid conditions. How could you tell if that aspirin would not be safe to take? Simple, you open the bottle and you quickly smell it. And if you happen to smell any vinegar-like smell, of course it's not like smelling a bottle of vinegar, but if you are able to smell any even faint smell of vinegar, you know that aspirin has begun to hydrolyze and would not be safe to take it. So I think it's kind of an important point to make here. For testing and recrystallization of aspirin, you will be using a separate data sheet available as a part of the handout on Canvas. I'd like to also point out you're expected to calculate what's called percent recovery, and percent recovery is not the same as percent yield. Percent recovery is found for recrystallization by taking mass of substance that you started recrystallization with and comparing it to the mass of the substance you're able to recover after recrystallization. And so you would divide mass of substance after recrystallization to mass of substance you started the recrystallization with, and then that gives you percent recovery. That's all for this one.